Last week we talked a little bit about named entity recognition, but we didn't had a look on it for today. So this is one thing I would like to present today, some very simple stuff about named entity recognition and how you can use some functions on text to find out what is the name in the text or what is the location. And this could be very useful, but we will see it's a strange structure of the data, especially for deep learning later. And the second part today will be about theoretical introduction into what is not really deep learning, but what is going on in artificial neural networks from an applied perspective. Because some of you said last week that you're not familiar with these kinds of algorithms, so I will try to give you an overview of this, and the overview is really focused on the question, what do you need to know in the end when you're applying artificial neural networks? So we will not go very deep into the theory or into the mathematics behind it, but it's quite useful to have an understanding of what is going on in these networks and how they work, what the different formulas are. I also uploaded a Jupyter notebook that you can see here. In addition, I put all the Jupyter notebooks, and I will keep on doing this on the GitHub repository, so you can clone it from GitHub if you want to. Posted the link on my blog, and I posted the link to my blog in Moodle. And on the blog you also find the first video of the first session, and soon there will be at least the second video, and today is our third session, so this might take a week or so till this video is available. But in the end you will find all the videos there. So, named entity recognition. I just noticed, because these are scripts I use for different projects I'm working on, and sometimes I just have some other rests from other projects in this notebook. The second line would just import a normalization function, which is very similar to the normalization we did in the first session. But I didn't upload the normalization Pi script, so it wouldn't work. But you can just, you don't need it. I just checked it. This function is not even called in this notebook, so it's no problem. You just can comment it out, then everything should work. You are probably familiar with pandas. Pandas is a very important library in Python that is used for all kinds of data frame manipulation. So when you come from R, in data science normally you are used to work with data frames, so kind of tables, and this is something that is not directly implemented in Python, so we need the pandas library to get nice tables in the end. Line. Man sieht nur meinen Kopf oder meinen Kopf nicht. Das ist ja schrecklich. Ja. Kannst du es mal drehen, dass es halbwegs passt. Kannst einfach hier ein bisschen mit Gewalt. Okay, I took an example text here about Bayern Munich. Bayern Munich is a German sports club based in Munich, Bavaria, Germany. It is best known for its professional football team, and so on and so on. And what we want to do is we want to identify named entities in this text. In the next line would be the second text example if you want to try out with different text. This is just again a part from the Wikipedia article about artificial intelligence, which I like to use as examples many times. So, okay. I was wrong, you need the function. I didn't saw it, sorry. So, what is missing for you now is the function pass document, but I can just show it to you. So this script is based on the text mining book again, and it's just a combination of all the different things we did in the normalization script, but it's just put in one script so that you can import functions out of the script. I don't have internet connection here right now, so it's for me not possible to upload it. But if someone has internet connection, probably someone has. I know it's too complicated to upload it. So, but you see what? Or should we do it? Why not? Yeah, I just take in. Who has internet? You got internet? So I just give you an USB stick with a script, and then you can upload it on Moodle. Okay. Give you an idea. Yeah, perhaps I have to log in then. So what the pass document function in the end does is it just first of all it removes the breaks from one line to another line and just replace it with a single space. And then it checks if the document is coded in Unicode or not. And if it's not in Unicode, it's coded in Unicode. And then the most important part is the document is tokenized using the NLTK tokenizer. So first in sentences, and then the sentences are tokenized into tokens.
Just normalization, right?
Yeah, just the normalization.
Okay. So,
Can you look out for me?
yeah, I mean, when I close it, it will log out because I open it.
Good, thank you. So now you get this normalization script on Moodle, and if you download it in the same folder, it should work. But we just take this pass document function, so in the end you just could take the sentenized tokenizer and the tokenizer from the NLTK package and just use it in this one. Good. We are looking for the chunks, and now we are looking for named entities. And what are we doing here? It's The point is, for all the text sentences in the chunked sentences, we just look if there is a tag, if our already chunked sentences has the attribute tag tree, and then we take the label. We create an entity name, and the function in the end that we use for getting these named entities is let's see it here. So when we are parsing the document with the NLTK tokenizer, we already have this information in the data. So for example, now we see Franz John is a person, Franz Beckenbauer is a person, Munich is an organization, but for example, Bayern is said to be a person when you just do it with the normal entity recognition that is already integrated in the sentence tokenizer of the NLTK package. But there is another NLTK model. You will have to download it from the NLTK page. It's the Stanford Named Entity Recognition model, and you need the model as well as the jar file to the model. So these are two files you have to download from the page, but when you have them, this English 3-class dissing blah 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 and the jar of the model. When you have them, you can run the named entity tokenizer. So it's Stanford named entity recognition tagger, and we just import this function as SN. And now, if you use this, it takes a little bit because the model has to be loaded first. If you use this, you see that it's quite good already. So Franz John is identified as a person, Franz Beckenbauer is identified as a person, Germany is a location, Bayern is an organization here, which is, I think, quite okay, because if you remember, it was an English text, so Bavaria is seen as a location, Munich is seen as a location, and FC Bayern and Bayern Munich are taken as an organization. So this is quite okay, but we already have installed a more powerful library for named entity recognition, and this is Spacy. We used Spacy last week, and Spacy is really good for named entity recognition and for visualizing what is going on there. So now we import Spacy, and we use the English core web model. In this example now we have to transfer our text in Unicode before we give it to our function now is the NLP function. So Spacy does many things in one turn, as you have seen already with the NLTK sentence tokenizer, who has this information about named entities in it as well. And same with Spacy, you just use the natural language processing function of Spacy, and now what we get is a list for all the labels that we have found. And you see there are different labels than before. For example, numbers are identified as cardinals, year numbers are identified as date. So this could be very helpful for natural language understanding projects. Altogether, our Spacy named entity recognition system found 39 named entities in this text. And now, for example, we can have a look at the labels. So we found 5 cardinals, 6 dates, GPE is the location. NORP, I don't know what it is right now. I would have to have a look. And we have persons and organizations as well. And most common, and here you see there was something wrong in the function I called in the beginning, because I explained that our normalization function is deleting these breaks and trying to replace them with a single space. So I think this has a I would have to go into debug and see why not. So this shouldn't be here. And now this is exactly the problem. We have identified just the break between the lines as an identity. This is something we don't want. But this here is something really cool that you can make with Spacey. So you can just print the text, and then you have the different labels for. So what you see this GPE all the time. These are our breaks in the sentence. They should be there, but now you see FC Bayern directly in the text is an organization, and the club is an organization. This is quite good. It's Spacey. And this is more or less everything I just wanted to show. It's not really... yeah, you can use Spacey, of course, as well to get some connections between the different labels you found. So, yeah. It's a dependency tree again. Is a verb, and the verb depends on or other things, and depending on the verb, or here Munich and FC are said to be, this is a conjunction of Munich. It's not working perfectly, like with all these things, but you get another dependency parser there. Here we got the list of all the words now with all the tags that we have found. And yeah, this is it. So you can make a dictionary out of it if you want to work later on bigger texts. You perhaps want to build a dictionary to have named entities in your dictionary directly, and then you can look up in the dictionary, or the computer can look up in the dictionary if you have found something that was already known or whatever. Some things are quite remarkable, like chunks like in the middle of the 1970s are identified as a date. So this is already a little bit of artificial intelligence. Or this is hard for a computer to identify this as an organization, the club. Just imagine club. Club has different meanings. It could be a baseball club or something like this, and it's the club is seen as an organization. So it is quite helpful. It works quite good, but again, when you use it, you have the problem that there are many mistakes in it. So even if it's right in 95% of the cases, and you run this on a huge corpus, and then you have, let's say, 1,000 entities found in this corpus, and in 50 cases you are totally wrong, then this is a little bit annoying. Yeah, so this is named entity recognition. Any questions to this? Then we're going to start with real machine learning now. So I uploaded some slides as well, but I'm going to present them here. Machine learning in general. So this is now a little bit really like a lecture, and then after this we have time for questions, and then we have time to discuss project ideas, whatever. But so what is machine learning all about? Machine learning is about finding relations in data, and there are different different schools, so to say, in machine learning. There's a big differentiation between unsupervised and supervised learners. Supervised learning is what we do most of the time. The idea is that you have already some labeled data, so you have data, and the input data can be quite complex. It doesn't really matter, but for every case in the data set, you know already what you want to know about new data points. So, for example, text classification would be a supervised learning normally. You have some different texts, and you know this text was made by the SPD party, and the second text was made by the Green party, and now you've got many of these texts, and for new texts you want to find out, make a prediction, is this text more likely made by the Greens or by the SPD? So this would be text classification task, and this is a typical supervised learning task. The idea there in supervised learning, and this is what we will focus on right now for the beginning, is you have your input data and you have output data. And now you're looking for a mathematical function that somehow transfers your input data into something that is very close to your output data. And then you can imagine that it's from the setting quite different if your output data is, like in this text classification case, a label, so the Green party or the SPD party or whatever, or if it is a number. Because from a mathematical point, it's definitely quite different if you want to estimate a number in a continuous space or if you want to estimate a label. And these are the two big fields in supervised learning. One is regression, one is classification. So when we try to predict a continuous number, then we are talking about a regression problem, and if we try to predict a classification, a label, then we are into a classification problem. From this idea that we have this input data and we want somehow find a mathematical function that transfers this input data into something that is very similar to the already known output data. You can imagine that we have different parts in this machine learning setting. So I normally say there are 3 different mathematical functions in machine learning, and we have to think about them together. We have our model, the kind of a function that is really fitted by the computer. And this could be very different. It could be a linear model. So this is machine learning. Yeah? You just take a very simple formula, just the formula of a line, and use this formula as underlying structure in your model. So there, the idea would just be that you are saying there is somehow a linear effect from my x variable or my x variable on my output. But of course you can use more advanced models there. And what we are doing with artificial neural networks is the idea is we are not really defining the whole model, but we define a structure that is very, very flexible, and we let the computer optimize the structure. And then we have the structure in the end as a kind of universal model that we can use for our predictions. But for the predictions we have a second part, a second mathematical function, which is called the loss function or sometimes cost function, because when we make a prediction we have to tell the computer in a mathematical way, was this prediction good or bad? How bad or how good was it? So we somehow need an evaluation criteria, how good our predictions really are, measured on the already known data that we have for our response variable. And this is not all. We want to do machine learning, so we are not defining the model and all the parameters in the model, but we want the computer to learn the best sets of parameters in a given model that we propose. So we need a third mathematical function, and this is an optimization function that, given a cost function and given a model, somehow optimizes the parameters in our model in a way that our input is transferred to the prediction. And this is more or less all that is done in machine learning, at least as long as we are staying in the perspective of supervised learning. Unsupervised learning, we will touch this later on. It's not so different from supervised learning. Once you have understood these principles, you will easily get a grip on unsupervised learning as well. So, as I said, a very simple function for a machine learning model would be our y, our response variable, is the result of a linear function. And you can imagine this in a two-dimensional space. So we have here our response, and we have here our predictor variable. And in many cases, this might be a good idea to say there is a linear connection. Somehow, when our variable gets higher values, then our response variable will get higher values as well. Or lower values could be a negative thing. But the whole pattern that we would find in this data now is really represented by this very simple formula. So we can describe the whole pattern, which is a line here, just by giving the intercept and the steepness. Is it called steepness? And the slope and the slope of the line. So each line is totally defined by the intercept and the slope, and this is all. Normally, we do this directly in matrix notation. So this means this A and this B might not just be one scalar, but it's a vector from the beginning. So we have a vector B that exists of many parameters, and we have a vector of x values, or x is a matrix of vectors where we have different values for different variables. Like, let's say we want to predict unemployment in different regions. This would be our y variable, and then we might have the BIP, we might have how many cars are registered in this area, and so on and so on. And for each single case, we would then have a different value for x0, x1, and so on until xn. But what we have in this formula is that we have just one parameter for all our x0 values. It's quite hard for me to estimate how much you already know of this. So if it's too boring, you just can give me a sign. But if you get puzzled about it, then it's directly the right point to ask something about it. So, as I said, we have a cost function. We have a model. We saw an example of a model on the last slide. Now we need a cost function. And a very simple cost function is that we take our predicted data, this is our hypothesis with H. So hypothesis better, and then X for all the different X's means these are the outputs of our model. And we just compare the outputs of our model with the given values of Y by just taking the difference. And if we would simply take the difference, this would mean, for example here, sometimes our prediction is too high, other times our prediction is too low. So the term from just taking the difference would have different minus and plus values, and these might eat up each other. And we don't want this, and this is why normally we take the square. So this is, and then we take the sum of all the arrows, and the simplest cost function would be just to divide the sum of arrows again by the number of observations, which is n in this case. So this would be the mean squared error. In machine learning, especially with neural networks, we often add a factor 2. This has some reasons, because out of the stochastic gradient descent we want to use, but you can imagine that it doesn't really change a lot about the idea. So the idea is you just take the difference between your prediction and the given values, take the square of the arrows and sum up the arrows, and then you take the mean. And what you are trying is to reduce this mean, and if you can reduce this, you have a very good model in the end. So, what is normal gradient descent? Gradient descent is works like this: that you make one prediction with your model. You have you normally start setting all the parameters in the model randomly within a touch of state one. So what you can do then is you can just make one prediction, then you calculate the gradient of your cost function, and then you see what in which direction do you have to change the parameters for your cost function. And then you define a learning rate, normally a very small amount, and you know, I started here, but I could get a better model if I change the whole, this is just meant to be a multi-dimensional space, topography. So it could be not just a two-dimensional space, but a three-dimensional space, for example. And we are looking for the local minimum, which would be here somewhere, or exactly here in this case. So from the gradient, we know now the direction, how to alter the parameters. Then we alter the parameters, but just a tiny, tiny little bit, and make a new prediction. And then we see, okay, where do we have to go from there, and so on. This is normal gradient descent method. In neural networks, we normally don't use the simple gradient descent method, but we use the stochastic gradient descent. And this just means that each time we make our prediction, we are not looking at all our data points, but we just take a random sample of our data points and make the prediction just for this random sample. This is then called a batch, or a mini batch, depending on which book you're reading right now. So, of course, this makes our predictions not as good as they would be in the gradient descent. Gradient descent is really as long as there is a function, for example, like linear model, then gradient descent really works absolutely fine, because the cost function of the linear model just has one minima, one global minima, and you always find it with gradient descent in. But the problems we are interested in, and especially the cost functions that come out of artificial neural networks, they might have multiple local minimas, and it's very, very difficult not to end up in a local minima. You want to find the global minima of your cost function in the end. Stochastic gradient descent is a way to avoid this, but as you can see in this picture, it leads to a fuzzy way of optimization. So you are not at all time taking the best direction. And this, in the end, simply means it takes longer. This is one reason why artificial neural networks are quite computationally intensive, because you always calculate the model many times on different batches, and your optimization process is not really optimal. But you gain something very powerful by this. You might jump out local minimas again. Otherwise, you would stay there. So, you only can do this kind of optimization when you have a regression problem. So if we don't have a regression problem, we need a different model and a different cost function. What is used quite often is a so-called sigmoid function. It has, the sigmoid function has really interesting properties. You have one parameter, t in this case, and if t gets very low, the result of the sigmoid function will be 0 or nearly 0. And if t gets very high, the result of the sigmoid function will be 1. So all the time you get a value between 0 and 1. And this is quite good because you can interpret this value as a probability. The probability, for example, that an observation belongs to a class. And this is why we use this in logistic regression. Logistic regression just means that we are using a regression model, as you can see over here in the formula, but we are putting this regression model into the sigmoid function or in the logistic function, and this has the effect that the results of our prediction will always be between 0 and 1. You can interpret it as probability. But, and we could really discuss this for quite a long, for many sessions. This is what I'm doing when I'm teaching the real machine learning course, and not about neural networks. It's really interesting that here what we are doing is we still have a linear model, and we just put this linear model into a logistic function. So more or less all the nice things about linear models, for example, that you can add interaction terms, that you can add higher polynomial terms into a linear model. You can do this with a logistic regression as well. For our ideas about neural networks, it's quite important to know this function, because this function is used many times as an activation function in the neural network. And logistic regression is what we do in the end when we try to make a classification in any kind of network. So it's always something similar to logistic regression. Let's look at the cost function that we get out of this sigmoid function. The point is, you can transfer our function here in a way that we get a cost function, which is okay. This cost function on first seems to be quite difficult, but the idea behind this cost function is, if you're looking at you get the minus y value, and our y values in a logistic regression case are either 0 or 1. So we have labels, and the label might be 0 or 1, and then there are ways to represent more labels. But even if you have more labels, you normally just do multiple logistic regressions. So for example, if we have 7 parties, then first label would be observation belongs to party 1, yes or no. Observation belongs to, if it does not belong to party 1, then it could belong to party 2 or to any others, and so you get a 0 and 1 coding. And here the point is, if you now take the logarithm of your hypothesis and multiply it with 0, with your 0 or 1. So if your observation is 0, then the first term gets 0. And if your observation is 1 and your hypothesis is 1 as well, then the whole cost becomes 0. So if you're, what you have to think about is your hypothesis could either be 1 or 0, and your y values could either be 1 or 0 in this case. Your hypothesis in the end will not really be 1 or 0, but it will be a value between 1 or 0, and the closer it gets to 1, the more likely is it that the label should be 1 in the end. So what you see here is this cost function really leads to a situation where the cost gets 0 if you have guessed the right label, and where the cost gets 1 if you don't have guessed the right label. And then we can take the gradient of this function and use this to optimize our logistic model. And this is a logistic regression model, and the picture is quite interesting because later on we want to work with TensorFlow, and one main idea of TensorFlow is that you can represent all types of mathematical function into a graph structure. And this is what we are doing here. So we have here our input variables. We have here the parameters beta. So each value of x1 is multiplied with theta 1 in this case, so with our parameter for this value. All these weighted inputs then are just summed up. Then we have our activation function. Activation function here would be then a sigmoid function. So this is our linear model. By the way, this is our intercept. We got an additional value here. It's not x, but it's 1 for each observation. And we multiply this one with theta 0, which is then our intercept from the linear model. We sum this up, we have an activation function, we get an arrow, and we have a unit step function that gives us an output in the end. So this is just here we get a value between 0 and 1, and here we just say, for example, if the value is above 0.5, then take 1, or if it's below 0.5, then take 0, and this would be our output. And this is a main idea about TensorFlow in the end, that you can represent all kinds of equations in a graph. And this is quite cool later on, because then we can say we are just defining what kind of inputs should be here, and we are defining the graph and how everything should be connected in the end. Then the computer can already calculate how much memory it needs for which operation, and so on and so on. And this makes it very, very fast in the end. This is already a kind of neural network. It's a logistic regression put in a graph structure. But it's really the same like this single perceptron. A single perceptron, this would be what happens in one neuron of an artificial neural network. So one neuron then is called a perceptron. And the idea is exactly this. We have our different inputs, we have weights, we multiply the inputs with our weights, then we have a kind of activation function, and if this function is activated, then we take it to a step function with a threshold, and the perceptron then gives an output of 0 or 1. Yeah, you understand the ideas about this? You also could say this whole perceptron is nothing else but a kind of function that transfers our input values x into 0 or 1. Activated or not activated. And this kind of perceptrons now can be combined in more complicated network structures. So what you have here is for every error, we have to calculate some weights. We get here our inputs. The inputs are then here first. So there might be a step of normalization, for example, from the inputs to the values that are really given to our network. And then this value is passed to all neurons that are in the next layer. And it's not just passed, but it's multiplied with different weights. So this weight could be different from this and this and this weight. So the signal is spread over the whole net, but it's spread in different ways. And for each neuron in each layer, we then have we have an activation function, and we calculate all inputs that come in here. Do they activate this perceptron, this neuron? If yes, then it will send a signal to the next layer. But the signal, again, is weighted differently by all the different weights that you have. One very cool thing directly from the start is there is no reason in a neural network that we only have one output variable. We might have multiple output variables, and this makes it very, very flexible for many, many cases. So in classical machine learning, we normally have one response variable, because classical machine learning is deeply depending on linear regression and all the developments out of linear regression. Here we can have multiple response variables. If we would cut off the network here, then we would even have more response variables than we have as input variables. This makes it very, very flexible. You can do crazy things with these kinds of structures. Yeah, some words about the notations. We got our incoming connections. We got our weights. Here we have a transfer function and an activation function. The transfer function normally is just a sum. Activation function, we will come to this because there are different activation functions and they have different, some are better for some cases and some are not so good. And then we have an activation value, normally called A, and this value is the outgoing connection. Everyone can follow? Good. First thing our neural network does is feed-forward optimization. So we have some input parameters. We have our loss function, we have training data, and we have a learning rate. And what we are doing is we take, for example, our labels and our features. Then we get a random mini batch out of the data. So this is stochastic gradient descent process. And we calculate an output. Then we sum up all the outputs from the gradient descent, from the stochastic gradient descent, calculate the gradients, and with the gradients we know the gradient then now multiplied with the learning rate moves the weight in another direction. So but the problem is, how do we get the right weights? So this is the big problem in our neural network. Feed-forward optimization, where we already have the weights, is simple. It's just a combination of a simple summation and multiplication issues. So, but how do we optimize the weights that we have? And this is called backpropagation, and it was a real breakthrough in artificial neural networks made in, I think it was 65, by a political scientist, Paul Werbers, and no one in political science knows him. This is quite interesting. But he is one of the most cited persons in the world when it comes to neural networks, because he invented this backpropagation algorithm. And the idea is, you start with forward propagation. So you just take random numbers for all your weights, you calculate your outputs, you have your cost, and then you do this already in a mini batch fashion, as we saw on the last slide. Then you have your outputs, and what you can do then is you take the gradient of the cost function, and you see how do you have to tweak in which direction the inputs of the cost function so that you get a better result. And then you calculate this gradient, and you go one layer back. So starting from our output, here we calculate the gradient of the cost function. Now we have, we know, these two neurons should become less in value or more or whatever. So the results from our gradient calculation. Then we calculate the gradients for these, and another step back, and another step back, and another step back. So we are starting to optimize our weights for our neurons from behind, and move back and back and back and back. But we do it in very, very tiny steps, and therefore then we have to recalculate forward propagation again and again. We do this with a mini batch to find the right cost, and not just a local minima. And then we do back propagation again, and forward propagation, and back propagation, and forward and backward, forward, backward, forward, backward, until the network is optimized in a way that we hope that we found a global minima, and all the weights are optimized then. And this really takes many, many iterations. And you can imagine it strongly depends, first of all, on the problem that you have, on the data that you have, on the scale of the data that you have, on the randomization of the weights that you did. So if you give all the weights the same value in the beginning, you will probably have a big issue, because when all the weights have the same value and you try to calculate the gradient, it will always be the same for all the weights. So you're optimizing all neurons in the same way, but you want differences in the neurons. So how do we initialize our network with random numbers? How do we calculate our mini batch? How big is our learning rate? If the learning rate is very, very small, we need thousands or even millions of iterations to find a minimum. But if our learning rate is too big, we might shoot over our aim and don't find any optimum at all. We might even come into a situation where the whole optimization process is not optimizing anything anymore, but it's really getting worse and worse and worse. So, the takeaway message here, yeah?
And why doesn't it get stuck in local minima? Like, it's still using these.
Exactly. We hope that it does not stuck into a local minimum, but we don't know this. But we can, what we can see, or what we can plot is, we can plot the loss that we have over the different iterations. And normally what we would like to see is that the loss is getting lower and lower and lower and lower and lower. And at a certain point, if it doesn't get lower anymore, we might be confident to stop the whole process. But again, this gives you another parameter in the model in the end. Then you have to define when do you want to stop the process. Or you just say, I want to run 10,000 iterations, no matter if the loss is changing or not. But still, it might be that you end up in a local minima. And this then, for example, from the things we have learned right now, would depend first on if the learning rate is too low, you might be in a local minima and there's no way to get out of it. Or if you set the mini batch parameters in a way that the batches are, for example, too big, and you are not doing enough of iteration for each batching process. But the takeaway message, therefore, is it is very computationally intensive. This is why neural networks, this whole theory is known, as I said, with backpropagation since the mid-60s of the last century. But it was never really used anywhere because it was not really working. On the one hand, if you had just some few data points, you were overfitting dramatically and ending up in local minimas all the time. And if you had a lot of data, then you could just not run these models because you would have to run them so many times and it was so computationally intensive that the computers just could not do it. And they were really, this is kind of pop culture of machine learning, but in the mid-90s there were really only a handful of people still working with these neural networks. And most of them now are rock stars and working for Facebook or Google or have their own AI institute in Zurich or whatever. But the point was really that no one was believing that you could really do something out of this very computationally intensive models. And there were other models in machine learning, kernel models, for example, that were very powerful at this stage. So no one believed in neural networks anymore. Let's have a closer look at the activation function, or different activation functions. So the idea of the activation function is the function gets as input the summed up inputs multiplied with the different weights. And now we want to see what do we give as an output. And this is what the activation function is. We already saw the sigmoid function in logistic regression, and it was traditionally used as the number one activation function in neural networks, because it's quite nice to have a value between 0 and 1. This means that after the first layer, all the values are on the same scale automatically, because then every value is between 0 and 1. And it has another very nice thing, the sigmoid function. Do you know what the derivative of the sigmoid is?
Sorry?
Do you know the gradient, the derivative of the sigmoid?
Sigmoid function into 1 minus sigmoid function.
Exactly. So if you have already your sigmoid value, the computer does not even have to calculate anything. Not much. It's 1 minus n. So, but this is an advantage because you don't have to calculate very complicated gradients. And you will see the same with the other functions. This is the tan function. It's still used from time to time, but most of the time now in neural networks, a ReLU function, a rectified linear function, is used as activation function. And there the idea is up to a certain point, the value that is returned by the function is 0, and after this point, the value is increasing linear. All these functions have some problems with gradients. Here, for example, I think we do it on the... Yeah, we come to this later. So these are different activation functions, and you could just come up with a new activation function and prove that it works better in one of the standard cases, and you got a paper published. And this is really what computer scientists do all the time. And it's it's a bit strange that in machine learning right now there is a lot of experience. For example, we all used to take sigmoid functions as activation functions just because it was hip to use sigmoid functions. And then someone said, oh no, now we use rectified linear function because it works better, and it works better on the cases they used to prove that it works better. And these cases came out of computer vision. So ReLU is a very powerful function in computer vision, but we are not really sure if it is the best function when we are turning to natural language processing. And the funny thing is that there are hardly any mathematical proofs why one function is better than another function, or in which circumstances a function is better than another function. So applied deep learning is really about trying out different functions, different parameter settings, and perhaps having a good or strange idea and try out if this works as well. Soft plus is similar to a ReLU function, but the point is that in the area where the ReLU gets close to 0, it has a little curve, and this makes the gradient in this area different. So here the point is, here the gradient in this area is always 1. So it's not possible, if you use the ReLU function for the computer, to make any kind of difference between this point here or this point here. But when you're here, it would be nicer if the gradient would not be 1, but a little bit less, and this is what you get out of the soft plus function. Different loss functions. Yes?
Are there optimizer functions? Which activation functions do you use?
Well, the problem is, if you really want to use which activation function is best, you have to calculate the whole model. And as we will see, we have to set so many parameters that calculating all the possibilities of all different activation functions with all the different parameters is beyond what can be done to that. So what is done normally is that you define perhaps different models, 10 different models or 20 different models or whatever, and try to get an impression what works good on your data, and then try to optimize 1 or 2 of these models that you have built. Different activation functions, loss functions. So again, for the same problem you could use different loss functions, and of course this changes the whole mathematical process in it. And this is again a parameter you have to define. Which kind of loss do you use? And it matters a lot. So for example, the first is really the normal mean squared error function, but you also could log your values, your prediction and your y values. And this might be very reasonable if you have in your response variable a huge scale, let's say from 1 to 1 million. And if you're logging this, then the differences are on a logged scale, and this might lead to better results. You could use an entropy function, or this function is a loss function you use when you have different classes and you don't want to make a logistic regression, but you want to have a probability for each class that your observation belongs to one or the other classes.
The X is for multiplication, right?
Yeah, it's a matrix multiplication. So these are vectors.
Okay. Yeah.
It's linear algebra.
I. So you have the index. Alright, so it's a number then. Or is it y I a vector? There are two indexes for y.
Here.
Sorry,
We
there
have-
we go. Thanks. Yeah. Okay.
Yeah?
So then you have this y is a matrix, two-dimensional. So yi is a vector. Yeah. Thank you.
When we're searching, this is something I already touched more. So this is really if you have a complicated function, the optimization field of this function really might look like this, so that it's not easy to identify the global minima, but there are many, many local minimas, and normally you don't get that. With these, for example, sigmoid activation function, you have problems with vanishing gradients. And this means as soon as you're somewhere here in this area, it doesn't, the gradient is not different from here, or if you are here in this area. So this was a problem with a sigmoid function, why everyone turned to ReLU later on, because ReLU, the gradient, if you are in the upper way, the gradient is always 1, but the values you get are different because it's a linear function. Here your value you get will always be 0, no matter if you're here or here or here or here, or it will always be 1. But with ReLU functions, you have the different problems. You might have exploding gradients that you are getting in your optimization process. Very, very high values and very high weights, and therefore you might jump from one local minima to the next and never come to the global minima as well. So this is the reason why all these ideas about optimization and activation functions this is really, many people are thinking about this, how to come up with better functions, and soft plus here is exactly a thing, quite new thing to optimize these problems that you have in the optimization functions. But again, no one knows if soft plus is really good for your case and for what you want to do, and it strongly depends on the scale of your data, for example. Then we have the problem of how to initialize our random weights. Again, I take the sigmoid function to explain why. The problem is, now I don't even need the sigmoid function. If you're initializing your weights and you have a symmetric structure in your weights by chance, so some weights have the same value, then they probably will be optimized in the same way all the time, especially if a whole layer of weights has all the same values. And then you cannot do anything, and you have to calculate a very complex structure with a lot of layers, a lot of neurons in the layers, but many of these neurons behave exactly the same all the time. So you would not even need them, and you make it far too complicated. So there are some functions, again, how to calculate the right random numbers for the initialization process. And this again is strongly depending on the different functions that you use. So as you could just use a uniform distribution, or you could use random numbers from a normal distribution. If you use a normal distribution, then the point is all the weights are normally distributed about the mean that you give to your normal distribution. This might be a good idea, because then you don't have some weights that are very, very high and others that are very, very low, but then you are running into the problem of symmetry again. If you use a uniform distribution, then your weights are uniform distributed about the space that you have defined. But this might then be a problem that you have the same high amount of high values and low values, and perhaps you set the scale wrong, and so on and so on. So again, there is a whole bunch of literature about this question: what is the right formula for initializing? So what is the right scale for the randomization process at the beginning? Yeah, then we have another leaky relu activation function. So here we had the problem that when you were with the normal relu function in the area of 0, then it stays 0 all the time. But if you make it leaking, then it is somehow a linear process, not with a slope of 1, but with a lesser slope. And the more you come into this area, still you get some differences out of your activation function.
Why are the derivatives of the old activation functions are positive, or at least 0? There is no negative one.
Yeah, well, it really does not. You could come up with a function that gives you negative values as well, but in the end, it doesn't really matter. It's just a number of it just would be on a different scale then. Yeah, and this ELU activation function. So here we got some negative values in this leaking functions as well.
Is the derivative still 0?
The derivative, yeah. This, yeah. But you could come up with a new idea of a negative derivative function and see how it behaves then in these networks. And it could make a difference. I'm not saying it's not making a difference. My first opinion was from the feeling, yeah, it shouldn't really make a difference because it's a continuous space and therefore it's just moving the scale somewhere else. But perhaps it makes a difference. Try it out. Could be a nice project. So yeah, but here exactly we have these functions give you negative values from the activation function. Next question, batch normalization, yes or no? And these are all questions when you build your models you have to decide on this, and this is why we are touching this. So you just could enter the data as it is into the neural network. What could be the problem then? Sorry? The question was, let's say we have as I said, data from different economic categories on very different scales, and we just enter these data into a neural network, and then we make our optimization process.
The covariance metrics that we will get wouldn't be correct because like depending on the scale, for some it would give really large value of the variances and some for really low, but it would be incorrect.
Yeah, exactly, and this leads to this situation. We are using the same learning rate on all the variables.
Yeah.
So we would all the time prioritize the variables with a high scale because our algorithm thinks it can make it better if we do optimization on x1 variable with a high scale, and we would not see that it would be nice to alter the other values as well. So this is the problem. Therefore, we need normalization. But if we do normalization, then the next question is, how do we do normalization? And these are the normal steps. So normally you just first take the mean, then take the standard deviation, and then you can use the mean and the standard deviation for normalization. But you could add some scale and location parameters as well. Perhaps you want to scale it in a way that all your data is between 0 and 1. Or you could scale it that it is that the mean is 0 all the time and the standard deviation is 1. Or you could scale it that the mean is 0 and the standard deviation is not 1 but 3 or whatever. So again, parameters, you have to decide in the end how to set them. And there are more advanced things as well called gradient clipping and weight clipping. Gradient clipping means you could just define a threshold where you say in my gradient, I only take values for the weights that are in this area. Or you could do directly weight clipping and say you define a limit for the weights. So it is no weight can go beyond 1. Or, no, this would be silly. Can go beyond 10 or whatever. Yeah. What else do we do to find the real optimum? Especially in the last 2 years or perhaps 5 years, but very, very recently, people found out that you can reuse trained models. So instead of training your own model from scratch, it's somehow, and no one really understands why, it's quite good to use a model that was already trained and not start with random weights, but use an already trained model. So the idea is, even if the model comes from a totally different area, the model has learned something very general if it was trained.
Mm-hmm.
And it's quite interesting to use a pre-trained model and then continue the training. For example, what they are doing now, machine learning models are using computer vision a lot. For example, for medical segmentation, we have pictures from how's it called? When they put the patients into this tube, MRI, exactly, and you get single pictures like slices through the body. And now you want to put these pictures together to a 3-dimensional model. And you can use machine learning for this quite easily. It's quite good results. But what they are using right now is many times they use models that were trained on YouTube videos. So they have nothing to do with any medical content, but it's just models trained on YouTube videos. They have learned something very general. They have perhaps learned how to differentiate between edges and spaces in the pictures. And yeah, we could do the same perhaps in natural language processing. And it might even be possible to use models, if they have the same structure, of course, that were trained on, let's say, computer vision tasks, to use the same initial weights for our models then later in natural language processing, and still it could work somehow. It sounds like magic, but the idea behind this is that a normal randomization process is nothing is really random in the world. So if you start with randomness, you definitely are very far from the real world that you want to model. If you start with a complex network where already things like, oh, there might be some linear effects, there might be some non-linear effects, and these effects are already trained in the model, then by retraining the model might just learn to switch these channels from linear effect 1 to B in a very fast way. So this was a very strong idea to use trained models already. Another thing that is done is freezing the lower layers, so that you just say, I don't want to train my lower layers. I take them, for example, from the pre-trained models. If you freeze them, then you don't have to calculate so much. You can do more iterations on the other things. And again, if you have many layers, it might be the more interesting things might happen on the deeper layers, because on the first layer you only can have linear effects from a mathematical point of view. Every effect on the first layer is a linear effect, or there is no effect. But on the second layer you can have non-linear effects and so on. And what really pushed deep learning and natural language, artificial neural networks into production mode was model zoos, so that there are already collections of different models, and you can just download the model and use them for whatever you want to do. And TensorFlow has a lot of model zoos, all the other platforms like Kefi. You find a lot of pre-trained models, and it was Facebook who really started to do this on a very high productivity level, and really categorizing every single model they had built in this company, and spreading these models all over the company for reusing them. Yeah. Okay, there's a very good book. I don't have it with me right now. It's called Deep Learning, and it's one of these O'Reilly books. And there you find all the different optimization algorithms again, because there are different ways of combining all these stuffs that we have. So, for example, right now many models use Adam as optimizer, but it's quite complex what is going on in this optimization stuff on a mathematical level. So if you are interested in this, go into this book. Adagrad was another very prominent optimization algorithm. But we have some other points. On the one hand, we want to have the best model. On the other hand, this stuff still is very computationally intensive, so we want to stop at a certain time. Perhaps we don't find the best model, but we have a good model, and then it should end somehow. Therefore, you can define early stopping rules with the out of back accuracy. And out of back means, because you're doing this mini batching, there are always some data points that are not in the model right now. It's only a batch. So you could just take the other data points that are not in this batch and calculate the accuracy the model has on this not seen data in this batch. And then you just can define a limit and say, when I reach an accuracy of, let's say, 95% in this out of back setting, then stop. Then it's good enough. And this helps against overfitting. Overfitting means that you have some patterns in the data, but they are just in this data that you have right now. It's randomness that is in the data, and if you build your model further and further and further, then your model will learn to represent this random noise that was in your data. But this is very bad for making prediction, because when you take new data, then this pattern won't be there because it was just random. Therefore, you have to do something against overfitting. Early stopping is not just good because of the calculation costs. It's good against overfitting as well. It's better to stop at a certain point and not to try to get another 0.05% accuracy out of it. Next thing you can do is regularization. Regularization means that you take an additional term into your cost function that is derived of the sum of the weights that you have. And the idea is then the computer tries on the one hand to minimize the weights, and on the other hand to optimize the still remaining part of the cost function. And by minimizing these weights, many weights will be set to 0 or nearly 0. It depends if you're using L1 regularization. This means you just take the sum of the weights. Then many of the weights will really become 0 in the end of the optimization process. And this means many of the connections, of the possible connections in the network, fall out. Perhaps some even whole nodes in the network will fall out. So you are reducing the complexity of the network, and by reducing the complexity, you make the network more robust. more robust against overfitting. And L2 regularization means you take the sum of squares of the weights and put this into the cost function. The big difference is in L2 regularization, because of the square effect, you normally never get any weight really put to zero, but very close to zero. For neural networks, the differences between L1 and L2 penalization are very subtle and don't really make a big difference. But you could use the same concept in other algorithms like linear regression, use penalization in linear regression. And there it makes a big difference if you use L1 regularization, which would then be called lasso, or if you use L2 regularization, which would be a ridge regression. Another thing you can do, and it's another parameter you have to set in your TensorFlow models later, is dropout. Dropout means every time you are optimizing your weights, you are not optimizing the weights for all the neurons, but you set a fraction of neurons that is not optimized at all in this round. In the next round, it's a random fraction, so next round, these weights might be optimized again, but from time to time, each neuron is not optimized. Why is this good? Who has an idea? What happens with this?
Regularization?
A dropout.
Oh, yeah, the dropout, we just randomly turn off some of the nodes in there. For example, like it can be multiple reasons. One could be that it's computationally really expensive. So if we want to like reduce the number of nodes and the weight calculation, the other could be that if we don't want codependence between different weights, then we can just turn few off randomly, so all the weights are independent of each other.
The second is the most important thing, because of course in one iteration you don't have to calculate so much if you use dropout, but it doesn't really pay off in the end, because normally you have to increase the number of iterations if you're doing dropout. But the other thing is really important. There might be a dependency between two neurons somehow. They got different, very similar values from the beginning, from our initialization process, and now they move in the same direction all the time. And so they don't give us any additional information. But if you break out this dependency between the two neurons by just optimizing one and not the other, then they might even develop totally different and move in different directions by optimization. And this then again adds normally a lot to the robustness of your model. So dropout really works very, very fine and should be thought of state of the art most times. But again, no one knows. So perhaps in your special case, dropout is not a good idea and you should not do it. And if you do it, you have to tell the computer that you want to do dropout, and you have to tell the right fraction, how many neurons should be dropped out in each iteration. And again, this makes a big difference.
Couldn't the computer just recognize, okay, these two neurons are basically doing the same, and then eliminating one?
But it could be good that they are doing the same. So it's really there are algorithms to analyze the structure of neural networks in their behavior. But this is really something that is done at the universities, and I don't think that perhaps beside Google and Facebook and Baidu, anyone in industrial setting is really doing this. There are many interesting ways of this, because you even can think that in the end the structure of a neural network should be somehow tell you something about the case and the whole model. So it would be very interesting if you really could analyze the structure of a trained model. But right now it's very, very difficult because of the random initialization, for example. It's very difficult to see what is really going on in the structure. There are some ideas like cascade networks, waterfall networks, where you get some information that you can identify in the structure of the networks on a level, and then you take this information and put it in another. But yeah. So most of the time right now it's just trial and error.
Maybe batch normalization could be a solution for that. It's like forcing the weights to be distributed in a normal sense, so they are like not most equal.
Yeah, but nevertheless, it could lead. You could have a situation. For example, when you have too many neurons, let's say you have a linear effect, a real linear effect, and you take 4 layers of neurons, then there is no additional information that these neurons can learn. So it would be good if they behave all in the same way. They should add nothing to the... And this is the problem there. Then you can... Data augmentation. This has pushed computer vision on a whole new level. But I'm not aware of any good ideas how to do the same. There are some ideas, but not so many, and not so many good, how to do the same with natural language processing. So the idea is, you have one picture of a strange mushroom here, and now you try to make more cases out of this one picture. And for example, you just could turn the picture a little bit, you could zoom in, zoom out, you could change the color. All these different kinds of manipulation you could do on one picture leads to a situation where you have many pictures where the pixels are a little bit different, and therefore the network probably learns better to identify the mushroom on the picture. And you could think about ideas how to do this with texts as well, but then you would have to change the text somehow. And how do you change a text in a meaningful way? This is not so easy. Yeah? You might combine different texts from the same area. You might change, look for synonyms and change words with their synonyms, things like this. But it's in a picture. Each pixel has the same meaning, more or less. And if you start moving the pixels to the left or to the right, you don't change really the meaning of the picture. But when you start fooling around with texts, it becomes different.
But aren't we doing this if we have to do normalization and tokenization, like with the different tokens, and like there's different tenses? Like we feed it like with the same sentence, but it's always in different, like we tag it in one.
But you don't change the data, so it's not data augmentation. You are adding, or you might add features or more layers to your data and say, I'm taking into consideration the post text, for example, yeah, and I'm taking into consideration the whatever. For example, named entity recognition does not really fit very well into this kind of structure of a neural network, because then you have, in our example, we had 39 entities and 11 of these were wrong because of this breaks. So we had some, I don't know, 100 or 120 words and some 20 entities. How do you want to represent this in a kind of matrix structure? You're always ending up with a very sparse matrix with a lot of zeros. This might not be so helpful then in the end. So it's very difficult right now to think about ways how you can use this algorithms on the complicated case of language. And augmentation would mean that you are changing the data, that you're changing the text, and synonyms is an obvious way you could do, but in the end you are adding something on a semantic level, and this might be wrong. For example, if you identify the wrong synonyms, then you make your model worse and not better. And here, it's quite easy to get more out of the data that you already have. Yeah, this is just an example. But last thing for today I would like to touch is, because next week I would probably start with word-to-vec models. Word-to-vec models are not deep learning models, as you will see, but they use neural networks, and this is what we have touched right now. The idea is you have a sentence and you have a window that goes from word to word. So, for example, here you see the whole window. In our example now we have 2 words before our word and 2 words behind our word. And now we just create samples. So, for example, always pairs. The word the appears together with the word quick. And the word the appears together with the word brown in this sentence. So now we have already 2 samples in our training set. We have the word quick as one sample and the brown as the next sample. And this goes on and on and on and on. And as you can imagine, you get a very, very large list in the end of all the tuples of words that appear together in the given context. And of course, the bigger you make this window, the longer will be the list. What we can do with this is that we just take our words as vectors. This means we just give each word that we have in our data set just a number. So, it means here, for example, we have our input vector is here, for example, there is a 1, and this means this is the vector for the word ants. So we just have it in a binary system with 1s and 0s. And then we have some hidden neurons. Normally in a word-to-vec setting, we have one layer of 300 or 200 neurons that we are using for predicting the probability of the other word. So that the word is, for example, the word fox. We had as input then the vector for the word fox, and then would use our network and the softmax function and calculate the probability that quick is a word that appears quite often together with the word fox. So here the idea is we have our input vectors, and we have here our matrix with our output vectors, and then we just can calculate from our input vector what is the right output vector. Or if you take it like this, the interesting point is when we train a neural network like this, then we have all these waves suddenly. And this means for every word we have, if we have 300 hidden neurons, then we have 300 weights that we have trained in a way that the weights point to the other word, to the other words that are close to this word. So what we can do is we take our input vector, we have our 300 features, we just take the correlation of our features and our input vector and run a softmax function over it, and in the end we get the probability that if you randomly pick a word nearby the word ants in the same vector space, it would be, for example, the word car if you compare car with ants. So what we are doing here is we use a neural network, in this case with normally 300 neurons, and we train it until it has learned everything that can be learned. So this means every time if the word car appears together with the word ants, then we want to have a 1 in our softmax function in the end. So we train all the weights in the network that at this situation we have a 1 because they appear together. But the word car does not only appear together with the word ants, but with many other words, and perhaps it does not appear very often together with the word ant. So these weights are in the end a representation of the position of our words measured by their probability to be close to each other in a 300-dimensional vector space. And with this vector space we can do a lot of calculations, or we could just use these vectors instead of the words and just put these vectors as input in our neural networks then when we want to build real machine deep learning stuff. Because then it doesn't really matter. Let's say we have two words that are very commonly used together in the same context. For example, son and daughter. If we have transferred these words in a vector space and they are close together in this vector space, then our model could learn something from these vectors, even if the word in the sentence is daughter and not son, the model would behave in a similar way, because now the input son and daughter is very, very similar, and it wasn't similar before. At the beginning, just every word gets a number. There's nothing else we could do with words, or we even do one-hot encoding. So this means we have a very huge vector with only zeros, and at one place there's a one, meaning this is the word. And this is what we would like to do in the next sessions, that we are starting to build our own word-to-vector spaces. And of course, there are already powerful trained word-to-vec models where you can just get the vectors for each word, and we will have a look how we can use these pre-trained models in our buildings. I'm not quite sure. I think I will, before we really do word-to-vec, I will probably put in a first hands-on TensorFlow session. So definitely for the next session you should install a TensorFlow. We will use it, and I will see if I find a good example for TensorFlow. The problem is the standard examples with TensorFlow, first of all, they are not about natural language processing, and second, they are always put together in a way that it's there's a data set where it's about handwriting recognition, numbers handwriting recognition, and all the difficult things like mini batching and so on, they are already implemented in this data set, so you don't have to do them. You can run the examples within 5 minutes, but you don't get a real understanding what you really have to do if you want to build a TensorFlow model. So I have to think about how we can touch this, but probably we just can't do anything in one session. So starting from next session, we will definitely work with TensorFlow.
I think in the first class somebody told that we can use some GPUs from like online cluster somewhere. Somebody was gonna like do a representation or something.
Yeah, I don't know who it was. Someone said, go ahead.
Yeah, I can't really remember how it works. I only know that they mentioned it in the deep learning course back then. But I think maybe at some point there was just some computers in the computer hall which have GPUs and which you can use, but I'm not sure. Like, actually wanted to figure this out, but I forgot. So maybe I could do it again, send you an email, and you can forward it to the rest.
Yeah, or you just can present it next week if you found something out. It would be interesting. Because it's the problem is I'm not really a local here at the Computer Science Institute. This is the only time I'm here, more or less. So I really don't know all the tricks what you can do here and so on.
And part of this, I think you can get like $300 free Google Cloud credits if you register to Google Cloud. But I think you need a credit card, so it's like a sweet option. But in general, my experience is you don't get such a big improvement or speed up with GPUs for NLP. This is mostly for CNNs and for computer vision because you have huge data, like you have mentioned. A single image with 3 channels consists of like I don't know 3 million flows or so, and a normal text with like 100 words is much less. So like usually you don't get such a big speed up with GPUs.
Well, this would be a very interesting issue anyway to think about, but I don't know the answers. In which cases does the normal parallelization that is used normally for computer vision make sense for natural language processing?
Yeah,
What you have said is one thing. The other thing is that especially when you start working with huge dictionaries of words, you have the data for a single observation might be much bigger than the data for a single pixel, and this could even lead into storage problems on a GPU that you wouldn't have if you don't run it on a GPU. So, but, my experience was that it's speeding up the things quite a lot, and I'm just using normally here my laptop with a GTX 980, which is not a very good GPU, and nevertheless I think it really pays to install the GPU version of TensorFlow if you have a GPU, but then you have to install CUDA and all the NVIDIA drivers and all this stuff. But you are computer scientists, you are good in things like this. For me it takes a week all the time to install CUDA. And I try to build TensorFlow from scratch, and I was hoping that then all the nice features my graphic card has would be recognized by TensorFlow, and I was working 2 weeks on this until it worked. And in the end, it's not faster than the standard GPU installation. So, any questions, anyone? I will plan to give you more time to talk about ideas of our project next week, so there will probably not so much input from my side, hopefully, next time. And thank you for joining.